Hi, I am DHARNIA, Assistant Professor in Department of Mechanical Engineering of Arya College of Engineering at IT, Kukas, Jaipur. Today we will learn about the different emission control technologies used for control of the SI engine emitted emissions. So let's we start. There is basically characterization of the emission control techniques are grouped into three forms. First one is engine design and fuel system parameters, engine add-ons to enable reduction of engine out emissions, and engine exhaust after treatment process. Engine design parameters. There are several parameters which affects the engine emissions. These are engine compression ratios, combustion chamber device design, spark plug timing, air fuel ratio, fuel system design, multiple valves, and engine temperature control. Engine compression ratio. The engine compression ratio affects the surface to the volume ratio of the combustion chamber, engine combustion temperature, thermodynamic efficiency, and fuel octane number for knock-free engine operations. The combustion chamber with a lower compression ratio has lower surface to volume ratio, resulting in reduction in volume of quench layer on the combustion chamber surface. The effect of surface to the volume ratio of combustion chamber shows that there is reduction in the HC emissions. Moreover, for a low compression ratio engine, the crevices volume would also be proportionally lower. These factors in turn would reduce HC emissions. Higher exhaust temperature resulting with lower compression ratio would promote oxidation of HC emissions and CO emissions in the exhaust system. At low compression ratio, the peak combustion temperature is lower and hence low NOx formations. Introduction of catalytic converters made the use of unleaded gas necessary, as the petroleum refinery economics receded. The use of unleaded gasoline of a low octane number, engine compression ratio had to be lowered. The principal disadvantage of lower compression ratio is that it has a poor fuel efficiency, then also results in higher carbon dioxide emissions also. High turbulence combustion chamber. By a small cylinder with hemispherical and pent-roof type combustion chambers are now more commonly used in SI engines. With the use of a hemispherical combustion chamber, the hemispherical combustion chamber, although may employ multiple valves, the two valves configurations is more common, as it is difficult to accommodate four valves at the necessary valve positioning angle. The valve heads along with the surface of combustion chamber from a profile that looks like a hemisphere. Both the intake and exhaust valve are inclined, increasing valve port area that result in high volumetric efficiency. The chamber also has a surface to volume ratio low. The intake ports are provided with a suitable curved geometry to generate high rate of air swirl, and the small cylinder engines can be operated at higher speeds with increases turbulence and tends to reduce HC emissions. Small cylinders have smaller amount of burnt gases that from high temperature adiabatic core. More heat transfer take place from the burnt gases. As the walls are nearer to the bulk gases, it results in lower NOx. And in pentroof type, pentroof combustion chamber being shallow compared to hemispherical combustion chamber, and it has somewhat higher surface to volume ratio. However, the pentroof combustion chamber is a good compromise between compactness of the combustion chamber and use of multiple walls. A shallow angle pentroof type combustion chamber allows optimum wall size and their positioning in the multi-wall engine configurations. The spark plug is also located close to center. Mixture from the intake port also across the cylinder to the walls from where it is deflected downwards directions and rolls perpendicular to the axis of the cylinder in a tumbling motion. This motion is called tumble. Multiple walls. 4 walls per cylinder are now common on the SI engines. The use of multiple walls increases wall flow area compared to the 2 walls. Spark can be placed centrally, reducing the maximum flame travel distance and hence faster and less knocking tendency combustions. Only one intake valve may be used at low speed and at low loads to obtain high intake mixtures, velocity giving high turbulence and swirl that improves combustions at light loads and high speeds. At high speeds and high loads, both valves are opens. The 2 intake valves may be provided with different valve timing and different valve lifts to obtain higher volumetric efficiency. The 2 valves may use different port designs to obtain the desired fluid motion in the cylinder. So these are the use of the multiple valves and in the helpful in reduction of the emissions. Next is variable valve timing and lift. A large valve overlap is required to obtain high volumetric efficiency at high engine speeds to make use of ram effect. At lower engine speeds, due to backflow of residual gases in the intake system, a low valve overlap is desired, or with increase in the valve overlap, residual gas fractions at low speed increases, giving lower NOx emissions, but HC emissions increases. Variable valve timing controls allows for continuously variable camshaft phasing over the entire power range of the engine. The NOx emissions with the fixed and typical with variable valve timing are compared in the figure. This is typical emissions with fixed the variable valve timing. The reduction of 30 to 70% in the NOx with variable valve timing are absorbed. Change in HC emissions between the fixed and variable valve timing is however small. The CO emissions however are a function of air-fuel ratio. Variable swept volume and downsizing. The passenger cars during the city driving operate at light loads when the high pumping loss, poor fuel efficiency and high HC emissions and CO emissions are obtained. Operation of the engine with lower swept volume would be a higher mean effective pressures, which would result in better fuel economy and lower CO and HC emissions. For 6 to 8 cylinder engines, the effective engine swept volume has been varied by deactivating the valve operating of half of the cylinder during city operations. This technology, although has been applied to 4 cylinder engines as well, but it is better suited for the large engine having 6 and 8 cylinders. Using of lower displacement engine and develop the required full throttle torque and power by supercharging is another approach to improve the fuel economy and reduce emissions, particularly the HC. At part loads, the supercharged and downsized engine can result in fuel economy improvements of up to 25% and accompanied benefits related to lower CO HC and CO2 emissions. So these are the basic technologies used for the reduction of SI engine emissions by the changing in the design parameters. Thank you.